We're going to do it with electronic workbench. All y'all have electronic workbench on your thing there. So this is what we got. We got 2 voltmeters. We got one measuring the voltage drop across R2. We got one measuring the voltage drop across the transistor. Then this is what we're going to do. We're going to change our voltage collector to emitter with this potentiometer right here. And notice what's nice on this one, we don't have to use 2 power supplies because our trainer either on the power sources uses a positive comm and the other one uses a negative comm. And that's why we have a negative positive power supply. So what we can do over here, these are our power supplies. So we're using plus 12 volts. This meter, this is an ammeter right here. This is going to measure our base current. This meter is going to measure our collector, our voltage collector to emitter. And what else do we need? So I'm looking at table 32-2. We're going to compute IC. We could measure, but we're going to do it just like the lab is. So this is a 100 ohm resistor. So we're going to use that to calculate IC. Of course, we're going to measure IB, even though we could measure the voltage drop across the 33K, but we're not. This don't have variable power supplies on it, so we're going to simulate a variable power supply by using a potentiometer. So we know we use a potentiometer now to adjust the voltage, right? And we're going to simulate a variable power supply over here with this resistor right here. This one I'm going to control with R1, R. This one we control with, this is going to control the letter R, and this is going to be controlled with the letter T on my keyboard. So let's see how it works. We'll turn on the simulation. And what we want to do is start off with first is 50 microamps, right? Now what we're going to do is we're going to generate our characteristic curves. We call them collector characteristics curves. We'll get as close as we can, close enough. Okay. So this is going to be our 50 microamps. And then what we're going to do is we're going to adjust for different collector to emitter voltages. So I'm going to adjust this one. I'm going to use T. And the first voltage we're shooting for is 2 volts, right? Of course, it's just as easy to go backwards through these. But that's okay. We'll go for it. Because it was already up to. Ooh, we're getting close. Okay, so let's go to program work. So we have 2 volts across here. We got VR2, which is measured. So here's VR2, 819 or 820 millivolts. We're going to compute IC because that's a 100 ohm resistor. And that's all we need. Are we okay? Is that everything? What do you mean? VR2, so this is our base current, 50 microamps, and that's given to us. This is our voltage collector to emitter, that's also given to us. And this is our collector current right here. So this is our voltage across our R2, which we're going to use to calculate IC. So IC is going to be computed, right? You understand that? So it's 820 millivolts. And no use using these, we'll just round it to the nearest whole number. So we okay? Ready to move on? Yep. Okay, so I'm going to come over and change I'm going to leave my current alone, and I'm going to raise my voltage up to 4 volts. Ooh, that's good. So now we got 841 millivolts. So notice, even though the collector to emitter voltage changed, the collector current is staying about the same. So y'all just measure the levels. Y'all can come back and compute IC in a little while, okay? So what I'm going to do now is I'm going to go ahead and go to 6 volts. Huh? This is 4. 841 millivolts. So VR2 is 841 millivolts. Can everybody see that? We okay? You can't, you just need to move a little closer, right? Got plenty of room up here. Y'all don't need y'all's computers anyway. And now we're going to go up to 6 volts. So this is 6 volts, 864 millivolts across R2. Everybody okay? Okay, then we'll go to 8 volts. Went over a little bit. Okay, so that's 8 volts, 886 millivolts. Okay, so what we're going to do now is take our base. Everybody okay? So y'all don't worry about calculating the collector current yet, right? Everybody okay? Alright. So now what I'm going to do is I'm going to change my base current up to 100 microamps. I think I just went by it. Okay, and we'll bring this deck down to 2 votes. Start the whole process over again. Okay. So there's 2 votes. R2 is 1.6 votes. Are we okay? So we're going to go up to 4 votes. Well, 1.7, 1.7 votes. If we R2 is 1.7 votes. Everybody okay? So we're going to go up to 6 votes. Yeah, it looks like it's, I'm good. I can't get exactly 6 votes. Okay. So 6 votes, 1.7 votes. Huh? Huh? Well, the other one's actually 1.65. This is 1.69. But it's going to be so close on your graph, it's going to be hard to go that many millivotes. If you look at the graph when you do your characteristics curves, it's over on page 277. You see. Then we're going to go up to what? 8 votes. And it's still 1.7 votes. It's actually 1.73 now, but see, it's pretty. Are we okay? Alright, so what we need to do is go up to 150 microamps on our base. So our characteristics curve is only going to have 3 things on it. Oops, I went too far. So 150 microamps, and then we'll start this all over again over here. So what I want you to notice is that even though we're changing the voltage drop across the collector to the emitter, the actual IC is staying fairly constant, right? It's the best we can do. So 150 microamps, 2 volts, voltage collector emitter, we have 2.3 volts. Is that okay? So that's the best we can do right there. So at 4 volts, we have 2.4 volts. Everybody okay? This is the best we can do right here, about 5.9. So at 6 volts, we have 2.5 volts. And at 8 volts, we have 2.5 volts. So when you do your so what are y'all going to have to do now? You need to come back and compute IC, right? For the 3 currents. And then you're supposed to do your characteristics curves over on This is the graph. What's the highest current that y'all calculated for IC? Y'all finished yet? Huh? What's that? What's that? What's the highest current y'all calculated for IC? $25 milliamps. So notice across the bottom they have the voltage collector to emitter set up for you, right? You understand? And up here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we can't use 17. So it's 25 milliamps. So what we probably need to do, 2.5 milliamps would be the thing, but that would be too hard. So we'll just set this off at 2. So that'd be 2 milliamps, that'd be 4 milliamps, that'd be 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, right? Y'all understand that? Yes or no? So what you're going to do is you're going to come up here and graph one of your measurements, like 50 microamps. So if we do 50 microamps, we would start off with one IC. And what you do is you start off here at 0, and then your first measurement might be up in here somewhere, and you'll come up here and you'll put a straight line. What's going to happen is you're going to come up here and you're going to end up with a curve that looks like this. And then what you do on this is you would write 50 microamps right there, and that would be your base current. So your base current is drawn on the line, right? You understand that? And what you're going to find out for our 3 currents, it's going to come up here and look something like that. Now in real life, they do a lot of currents. And what that means is, what we would do is we would come over here and we would set a spot where the transistor's saturated, and then we'd set a spot where the transistor was cut off, and then we could come up here and we could draw a line like this. Now if we wanted to operate this as class A, then we would try to bias our circuit so our collector voltage was exactly in the center. Y'all understand? So that way it could swing as positive as much as it could negative. And then we could literally come over here and put an AC signal on the input on this side, and then we could come over here and we could figure out what signal, what we would get out of this thing on the bottom. So y'all see how y'all going to do y'all's load line? Are y'all okay? Or it's called a characteristic curve, but when we come up there and put that line across there, then that comes up and actually sets up where the transistor can actually operate. So characteristic curves are really, really neat. And the book says they're included in your data sheet, but I've never seen one that is included in a data sheet. But using the beta and this kind of stuff, you could actually come up and you could develop the characteristic curves.